Hello, good evening, and welcome to a new food4Rhino webinar. A long time we don't see you because we had many events lately, but we have today the pleasure to have with us Andrea Rossi. Andrea is an architectural researcher and computational designer, currently a research associate at the Experimental and Digital Design and Construction Chair at the University of Kassel, while also completing his doctoral dissertation at the DDU Digital Design Unit at TU Darmstadt. And his focus is on combinatorial and circular design strategies, robotic fabrication and architectural biomaterials. And Andrea Rossi is the developer of Wasp. This is the software, the Rhino Grasshopper app we are going to see today. It's an open source Grasshopper plugin, as mentioned, for combinatorial design. And it allows users to represent and design anything with discrete parts. Remember that this webinar is being recorded, so if you miss a part of it, it will be available on this same link right after it finishes. And that there is a chat. Feel free to use it because I will be collecting all your questions and comments so that I can pass this to Andrea during the last 15 minutes of the webinar. And yeah, again, don't be shy. You can post there anything. If it's something that I can stop Andrea in the middle of the webinar, I will do it. Otherwise, again, we will wait for the last 15 minutes. So I hope you enjoy this new food4Rhino webinar. Many thanks, Andrea, for being here and for your time. And we are ready to see your presentation and Wasp.
Okay, great. Thanks, Carlos, for the introduction. And I mean, thanks for the invite. It's like super cool to be here and to be like kind of presenting some of the work I've done, which, given the fact that I think my last 10 or 15 years of work and research are pretty much entirely dependent on McNeel softwares. And so in a sense, it's something that makes me really happy to be able to present some of the work that I've been doing there. So what I'm going to try to do today is I'm going to try to have a short presentation, which I hope you can all see, which will discuss a little bit the ideas and the motivations behind Wasp and kind of a little bit why I've been developing this tool and what's this kind of context in which this is collocated in terms of architectural research. And then I'm going to try to do a little bit of a demo. First, I'm like just showing you a little bit what are the basic building blocks of Wasp. And then I'm going to try to go through some of the example files that are available together with Wasp to give an overview of what Wasp can do. And if we have time, I'll maybe show you also a couple of features that are just coming out right now with the new beta versions. As Carlos mentioned, I've been really busy finishing my PhD over the last few months, so the development have been a bit slow, but now the PhD has been recently completed, and so I'm happy to kind of let you know that there's going to be also more development coming soon. So briefly, as Carlos already mentioned, about me, I'm a computational designer and I'm trained as an architect. And really a lot of the interest that I have has to do with finding ways to think more open and more accessible ways to design, but also to fabricate architecture. And so in a sense, Wasp fits within this thinking and this logic of doing, as it tries to look at a way to think as design, not as a closed act of creating a single object, but rather as an idea of looking at design as creating systems. So whenever we are trying to look at this idea of how we can build systems that can be adaptively changed and interact by the users, we have first and foremost to have to talk about parts. So we know, as we all know, buildings, as anything in the world, pretty much are made of parts. And these parts are combined in order to create a functional assembly. Now, the problem that comes with parts is that the way in which parts are defined, it has a fundamental impact on what you can actually do with them. And what I think it's interesting is that the model of parts that we have in architecture today kind of dates back to modernism. It actually comes from even earlier, but specifically within modernism, we have this idea of parts and of modularity that is fundamentally functionally defined. What I mean for that is that the different parts of a building, they are defined based on the function they have in the assembly. So a column has a specific shape, and if you think about reinforced concrete, it also has a specific reinforcement layout that is very specific for that column behaving as a column. A floor slab has exactly the same system. It has a very specific geometry, a very specific material properties that are tuned particularly for that one to behave as a slab. And that's the same for foundations, that's the same for stairs, for facade elements, and so on. Now, what's the problem with this idea of parts defined functionally is that from one side, they give us a very specific definition of architecture that what's make modernism successful and famous about it. But at the same time, the fact that these parts are functionally defined and they have this very fixed definition of what they can and cannot do, it means that, as we all know, a lot of buildings that resulted from modernist design, they are extremely rigid, extremely inflexible, and they are extremely hard to change. And on top of that, if we look at a recent discussion about circular design, when building components are designed to perform one very specific function, it becomes very hard to think about reusing them for other functions or in other buildings. So what I think is also interesting is that the same idea of functionally differentiated parts is very much at the base of probably the dominant software paradigm in architecture today, which is building information modeling. So in building information modeling, everything is made out of discrete parts, walls, slabs, stairs, facade panels, and so on. But those parts are all functionally defined. So a window has a specific function, it has a specific position in the assembly. And what it means is that a BIM model, it's a highly hierarchical structure, which as part of the reason why changing and modifying BIM models, it often becomes extremely hard and requires a lot of effort in order to modify them. So if we want to think about a model of architecture that is more open, that could be changed during construction, after construction, that could also be adapted to the different needs of the users, we might need to look for a different model of modularity and a different way of defining parts. And one really good example, I think, is against the, let's say, functionally defined part that we know from architecture. We could look at a digital pixel. A digital pixel per se is a generic piece of an image that per se does not have any specific function. However, by kind of being next to other pixels and based on the brightness and color that this pixel has, it does assume meaning and a function based on the way in which the pixels next to it react. Now, what this means is that we need to try to look at parts that are digital, not in the sense that they exist in a digital media, but rather in a more deeper sense of the digital, in the sense that they are discrete. So they are made of parts that are generic in nature and that they can be automatically switched and replaced and recombined in a variety of functions. And this bears a lot of kind of the similarities and ideas on the way in which the difference that exists between an analog signal, where the different values kind of fluctuate very differently, and a digital signal, where by discretizing things in the individual tiny bits, we're actually able to transmit that message more reliably. So in a similar way, if we can break down architecture in parts that are generic and very simple, we can very easily simplify the process of fabricating and the process of doing that. So fundamentally, a lot of the work that I've done during my PhD and that then kind of fed into Wasp as a tool has to do with this idea of moving from an architecture made of functionally differentiated parts towards an architecture made of generic parts. And what that means is that rather than having elements that perform as a column, as a wall, as a slab, and so on, we have elements that are per se generic, but according to the way in which they are composed and connected to other elements and other parts in the assembly, they come to assume a certain behavior. So rather than having a column, we have a combination and assembly of those parts that behaves like a column. We have an assembly of parts that behaves like a slab, and so on. And what's interesting is that this idea is kind of new for architecture, but it's not in other contexts. And there's this very interesting concept that comes from the MIT Center for Bits and Atoms, from the team of Neil Gershenfeld, that is the concept of digital materials. And what this concept has to do is the fact of thinking about materials that are made of discrete building blocks, which have discrete joints and occupy discrete space. And if this sounds a little bit abstract as a description, if we look at a couple of examples, I think that becomes much clearer. And I think for sure, the best example you can think of is a Lego brick. So a Lego brick is a discrete piece. It fits into a discrete specific grid. It has discrete pins that allow them to connect just in specific ways. And that is why a Lego brick enables a kid to produce a very highly precise structure, even though a young kid has a very imprecise ability to assemble things. DNA and RNA chains work in a very similar way and allow to transmit information very reliably in a very unreliable environment as the inside of our bodies. And why these elements are interesting for architecture is that they have three fundamental characteristics as they've been defined again by the team of Neil Gershenfeld. And these three characteristics are programmability, reversibility, and reliability. What programmability means is that it means that by composing these parts in space, as these parts are generic, they can be kind of assembled, and this process of assembling them into a structure, it's in a way a process of physical coding. So what this does is it highly simplifies the process of assembly and the process of describing this assembly, as we are relying both on the same description, both in the digital world and in the physical space. Another fundamental concept that it's becoming of paramount importance in right now under the pressure of climate change and the consumption of materials is the concept of reversibility. Digital materials rely on the logic of being able to be reversibly assembled and disassembled, relying on discrete joints. And what this means is that they can be used to assemble a variety of structures, and then they can be disassembled and reconfigured. And this is thanks both to relying on discrete joints, but also on relying on repetitive geometries that allow to be reused for a variety of functions. And lastly, reliability, which again has a strong impact on architecture, deals with the fact that these models, given that they rely on a discrete grid which has fixed position in space, they're able to integrate error correction capabilities. And what these error correction capabilities do is they allow to very simply use a variety of assemblers to build the structures, as the precision is entirely in the part and not in the assembly system. Now, if this is a concept that is very interesting and comes from the field of material engineering, what about architecture? Now, in architecture, discussing generic parts is actually not it's not a fundamental element of architectural discourse, but there has been some key figures in this discussion, coming both from the field of engineering, such as Konrad Waxman and Fritz Haller, as well as from the field of architecture, such as Yona Friedman or Moshe Safdie, that imagine these assemblies of structures that are made of modules that are generic and that can be recombined and create a variety of different systems. And more recently, some of the key figures like Gilles Retzin and Jose Sanchez proposed to update these methodologies to the digital domain. Now, I've been always particularly interested and drawn to this kind of work, mostly due to the fact that it proposes a model of architecture that is very open and accessible, and that can be easily interact with the users, can be modified and transformed in a variety of ways. And however, when I started working on Wasp, at the time, there was a lack of tools to work on this. I'm happy to see that over the last few years, there has been a few other tools emerging to tackle these combinatorial design problems. But at the time, it's around 2017, there was a lack of tools to do this. There were some tools that were able to do some specific things. And so there was the reason for developing Wasp, which is, you could call it a discrete design or combinatorial design toolkit for Grasshopper. Now, Wasp is built on a very, very simple assumption. And the idea is that Wasp's parts allows you to define parts as closed mesh geometries. And on these parts, it allows you to define connections, which are oriented planes, which specify where another part can be connected. Once this is done, you can then start defining rules that define what can be connected to what and how. And then what Wasp allows you to do is to very quickly move from the process of defining these parts and connectivity rules to the process of generating very large structures. Now, you see here some of the work of some of my students. And what Wasp also does in the background is, of course, takes care that these connectivity grammars you specify are respected, but it also takes care that these parts are not colliding, that they always kind of come together at the right place, and so on. And you see here some of the works, and you'd see that most of the works have this kind of very chaotic nature, and that's because they're creating using a stochastic procedure. So a process that at every step picks a new part to place, a new rule to execute, and kind of grows into really this cloud. So what was necessary if this tool was to be used not just to create, let's say, crazy shapes, create a cloud of parts, but also to kind of have a level of control that would allow you to design with it. It was needed to find a way to kind of allow to embed design intent and design control to these aggregations. And in order to do that, I rely on a concept that you probably are familiar with, which is the concept of voxel, which is nothing else than the translation of a pixel in a three-dimensional space. Now, what Wasp allows you to do is it allows you to first create voxel fields, or let's say scalar fields, where you have a grid of points in which in every point to every point you can associate a specific value. And you can do it in a variety of ways, like, for example, here by simply measuring the distance of each point from a driving curve. And what then Wasp is able to do is able to grow the aggregation from the highest point of this field and slowly kind of follow the highest values along it that can reach within the grammar that you allow it to do and create and approximate the given field. So that can be done with distance, but it can also be done with any other three-dimensional scalar field. So in this case, you see an example in which using topos, a topology optimization was done, kind of finding the ideal materials density for a given load and support condition. And then this field, this material density field, was then used to drive the growth of an aggregation that would discretize this field. And so what Wasp allows you to do is it allows you very quickly to move from the process of designing the parts to the process of exploring what kind of structures and what kind of atmospheres these parts allow you to create. And so you see here some work at different scales. This is mostly work from students at the Technical University of Darmstadt, with whom we explore different models and also what this idea of an architecture that would be more open and made of parts that could be reconfigured would look like. And so we looked at different scenarios to use these modules both in urban context and as well as more rural context. But then, let's say during the research, it immediately came to our attention and to the idea. We came to the idea that if the idea was to create a more open architecture, it would be really good to kind of have a more open discussion about that. And so that was the idea where Wasp was released as a free plugin. And looking at the idea of creating not anymore just a plugin per se, but really looking at the possibility of creating a design platform where different users could kind of come together and design systems and share them together. And so what happened is that, very interestingly, as by publishing the plugin as a free and open source tool on food4Rhino, it immediately became a lot of different applications came to exist. Like in this case, in the Discrete Future Studio at the University of Texas, where students explore possibilities to reuse abandoned or vacant buildings and creating this kind of parasite structures around them. Or in this case, in the work of the AA Visiting School in New York, where students were able to think about this idea of discrete structures or reconfigurable up to the point in which the structures could be made of modules that they themselves had ability to move and transform itself and redesign and reconfigure themselves. Or again, in the work here, some work at the University of Innsbruck, where students were actually exploring what's the threshold between order and disorder in a modular system. And we're really looking at the possibility of using the same system, which you can see here, both in the right and the left of this image. It's the same exact modular system, but how by just adding one rule, and that's the rule number 46, that the system kind of transitions from the idea of order to idea of chaos. And so there's really this idea of using discrete system to combine very different topologies into a single coherent structure. And so given that, as I mentioned already, the idea was really to have this more open conversation about what this more open model of architecture could look like, Wasp was not released just as a free plugin, but it was also released then as an open source toolkit. And the goal of that has been very well defined by the developers of Ladybug, was to rather move away from the idea of thinking Wasp as a simple tool that solves all problems, to kind of try to look at Wasp as just a part of a toolkit which could then connect to a variety of different software tools, which could be taken and adapted into other tools and connected to other processes and so on. And so that was made possible by releasing Wasp as an open source project on GitHub. And what that did is it also created the possibilities for other researchers and other developers to build other applications that were either on top of Wasp or were able to communicate with Wasp. As in this case, a really great project from Jan-Philipp Druth from the Digital Methods in Architecture at the University in Hanover, which developed Project Disco, that is open source as well, a toolkit to bring Wasp aggregations into virtual reality and to kind of work in virtual reality to assemble those structures in a first-person process. And you can search the website. The tool is fully available. You can try it out. Recently, it also added the possibility of doing this in multiplayer, so you can have multiple users, and that's a very interesting project. Another great project that I've been involved with that also emerged out of this Wasp being open for modification was the conceptual joining project at the University of Applied Arts in Vienna, which was developed mostly by Lukas Allner and Daniela Kronert, where the idea was to push Wasp to its boundaries by trying to create aggregations using found branches that were 3D scanned and were by nature all different. And so the idea was, how can we use Wasp to create aggregations of parts that are unique? And so there was a process of adaptation that was possible because Wasp was open source, that was then adapted tool in order to be able to work with this very specific geometry. And this is a relatively old project, and there was quite a few things in this project that would be very interesting for Wasp. And I'm right now slowly starting to look into it again, and hopefully they're going to come out as new features in the future, in a future release of Wasp. And as well as the Wasp++ toolkit by Blake Hageman from the Illinois Institute of Technology, which very interestingly developed a set of really cool tools to kind of do certain things with Wasp that were not available in that current version of the toolkit at the time, and was able to kind of just take the source code and develop this add-on that was then available on food4Rhino as well, and kind of do that entirely independently from me. And so that kind of really shows this potential of adapting this. And last but not least, what I think it's very interesting when we start looking at the way in which we can design with Wasp is that Wasp combines in the background two things. So from one side, there's a geometric representation, which is what you are working with. And that's what you deal with on a day-to-day basis when you're working Grasshopper and creating structures. But on the back, Wasp also relies on a existing data structure that is kind of a parallel of the geometric representation. And what is very interesting is that this data structure can be easily, and it's going to become easier pretty soon, can be easily accessed, can be saved, can be shared. And so what I'm trying to look into more and more towards the future is this idea of making every part of a WASP definition shareable. So you would be able to share your parts, share your fields, share your aggregations, and create really this idea of a platform where different elements could be freely passed from one user to another one, and create this more open design and fabrication ecosystem. And what this also allows you, this underlying data structure, it allows you very quickly to do translations. So it allows you to translate from a digital model to a physical assembly process, as we were doing with our students, where we try to very quickly go within a period of 3-4 weeks from not even knowing Rhino to being able to generate discrete aggregations using Wasp, to then be able to translate them into robotic motions and assemble them in physical space. But it also allows to do other translations. Like in this case, we relied on the hologram Grasshopper plugin to translate a Wasp aggregation into a HoloLens hologram, and then guide users to assemble a structure, even though they had no idea of what the final structure would be. As well as this data structure in the back allows you to do exchange with other software tools. In this case, you can see here the results of a design studio that I was teaching with Sajay Bhushan and Johannes Megens at the University of Innsbruck, where we developed a pipeline that would allow to translate from a discrete model in Rhino and Grasshopper using Wasp into a very detailed and very complex mesh model that was done in Maya. And so again, building a pipeline to exchange between these different softwares. So this was a little bit of a summary of what Wasp can do, and I'm gonna go a little bit more in detail by giving you a little bit of a demo. As I mentioned, Wasp is free and open source software, and I'm trying my best to maintain it and develop it further. As I mentioned, I'm happy that my PhD is now completed, so I have more time to work on it. But of course, there's always a bit of a struggle there. So if you are interested and you like what you're doing and you want to support Wasp, there is a Patreon page where you can do so, and also get access to some additional video tutorials and resources that are just not available otherwise. And so that's kind of it. These are like handles, social media handles and contacts that you might want to use. We're going to have, as Carlos already mentioned, questions at the end, but also if you then want to reach out and talk about anything. One important resource that I would point you to is the YouTube channel Temporary Autonomous Architecture, where you have right now up to 20 video tutorials that will guide you through learning Wasp from zero up to relatively advanced features. And you also can find development logs where I describe some of the new features that I'm developing, or that as soon as they're coming up. And so that's just a very good resource. So that was it for the presentation per se.
Very nice, very nice. Just one comment.
Yep.
By Eren Otsuldash. He asks if there are tutorials on Wasp YouTube page still relevant, or else there for older versions of software. So, I don't understand the question. I mean, yep, I don't know if it's asking for tutorials for an older version of Wasp, or
yeah. So most of the tutorials that are on the Wasp website, they are either for version 0.2.8 or for version 0.5. One of the first things I'm going to try to do in the next few weeks is to make sure that there are example files attached to those tutorials that are relevant, that are from different versions. So at the moment, I know there's a bit of a problem, because although the interface changed very little, the older Grasshopper files do not work anymore with newer version of Wasp. So that's one of the things that it's on my to-do list already, which is to make sure that you're going to have a link to the newest example files.
But anyone can install the latest version, right?
Exactly, yeah.
So there's nothing that prevents a user to install the latest version.
No.
Only that maybe some tutorials are old now.
Exactly.
newest version, right?
Exactly. But that's something for you to know. There is also one video on the channel which shows you how to update old files. So there is one component in Wasp that is called update file that would actually go and replace all the old components with the new one that you have installed. So if you cannot use that, it's not really my idea. It's almost entirely taken from the Ladybug team, but that's a very useful piece of tool that allows you to do that.
Okay, thanks.
All right. So going forward, what I thought of doing is to first of all show you the simplest and most basic Wasp definition you could create. And then we're going to go through some of the example files that are available with Wasp to kind of see a little bit more how the features work. So to create a Wasp aggregation, you need very little information. So all you need is you need a part, which in this case is this hexagonal prism that I've modeled in Rhino. And then in order to specify how this prism can connect to other prisms, you have to specify connections. And so to specify connections, you have to specify two pieces of information. And one of them is the location of that connection. But then since the location for connection is a plane, you also have to specify the orientation of that plane that kind of defines if, for example, the next prism can connect like that, or like that, or like that, and so on. And so you can do that by making a plane directly in Grasshopper, or you can do that by using a line. And so what you can do is you can simply draw a line in Rhino, and you're going to be able to access that. Now, let me just find Wasp. Here we go. So once you have all this information, you can very quickly create your first part. And the way you do that is that you go to the Parts tab, and you get a basic part. And so what you need to do is you need to give it name. And I'm going to call it, for example, Exa. Now, names are case sensitive, so just be careful that if you do it uppercase or lowercase, they just match everywhere you use them. You then need the geometry, which is simply your geometry here. And then you have to specify connections. And connections are can be created from the information you have by just going to connection from direction. And again, specifying the geometry of your part, the center of your parts, and the up direction. And so you'll see that that creates automatically a connection object, but it will also create, you can see the planes where this connection will happen. And if we now go and connect this connection to connection, we have created our part. And you see that right now we have a part that is called Exa and doesn't have any ID because the ID gets assigned as we aggregate. So after we created our part here, what we can do is we can very quickly go and go to the aggregation tab and get a stochastic aggregation, which is, let's say, a fancy word to say a random process. And so what we need to specify is what parts we want to aggregate. And so in this case, that's going to be just our parts. We're going to have just one part for now. In Prev, if you want, you can specify something you have already aggregated. So for example, if you had created an aggregation in advance and you want to continue that, you could actually plug it in there. But for now, we're just starting from scratch. You then have to say how many parts you want to create. And so I'm going to start, for example, with 120. And finally, we come to probably the most important part of Wasp, and that are rules. So you have to specify how parts can connect to each other. Now, there are a variety of ways. Sorry, I think I froze. So there are a variety of ways in which you can define rules. So you can type them manually. You can define them with a component. But the easiest way to do that is to just go to the Rules tab and get a rule generator. So now what a rule generator does is just takes all the parts in your aggregation, and then it has a few settings that will allow you to control how rules are created. By default, right now, we have a very simple part, which just says 3 connections. And what this is going to do is, by default, it's going to just create rules that connect every connection to every other connection. You can control through here if you want to just allow some of them to connect, just a part connect just to itself or to other parts as well, even for the connections. And then you can work with types and grammars that we're going to have a look maybe a bit later. So what I'm going to do is I'm just going to take my rules and plug them in rules. And now you see that even though you don't see anything yet, Wasp has already calculated. And if I go here, you see that I already have 120 parts being calculated. So what we are going to add extra is we're going to add a button that we're going to plug in reset, and we're going to talk in a moment about it. So now that we know we created this aggregation, we want, of course, well, see it. So what we need to do is, if we have our parts here, we need to go to parts and say get part geometry. And so when we connect it here, you will see that we can actually already very quickly visualize our aggregation and see how that's created. Now, one of the things that Wasp does a little bit differently than the way in which Grasshopper usually works is that if you're used to Grasshopper, Grasshopper has this logic because it allows you to edit all the steps of a process, that every time something goes through a Grasshopper component, it gets recalculated entirely. Now, Wasp does not do that, but what it does is if, for example, I change my parts from 120 to 200, it's not going to recalculate the first 120. It's just going to keep them as they are and just add the last 80. And that's, of course, done for two reasons. First one is for performance, because you don't want to recalculate everything every time, especially if it's very large. But also because what you can do is you can change the rules and, for example, constraints and different level things you use to control your parts during aggregation. So you can do the first 100 parts with a set of rules, and then you can switch the rules and use another, create another 100 parts, and so on. And this was actually kind of buggy up to till recently, but the latest version of Wasp that it's right now in beta on GitHub has actually fixed that, and it's working quite well. So you're actually really able to change rules as you go along and kind of create different areas of the aggregation that behave in different ways. Now, the reason why we have this reset button is exactly to deal with this process. So if instead you don't want to have the same aggregation, but you want to change it and create a new one, you can just hit reset, and that's going to recompute the full thing. Now, one question that I get very often when looking at this kind of processes is that a lot of times people like users might tell me that, okay, I was working on my aggregation and I found one that I liked, but I wanted to check something else. And then I hit reset again, and then there was no way for me to go back to the existing one. That's why Wasp implements a seed input. With the seed, you can block the random function that runs inside Wasp. So for example, if I put a number in there, I will put 25, for example, and I will then reset. Now, no matter what happens when I reset this aggregation, I always get the same result. And so this is actually something quite cool to use if instead of using a button, you use a toggle. Because what it allows you to do is it allows you to, if you keep that always on true, it allows you to kind of go and use this slider to navigate through all the possible aggregations you could actually do. So I know a lot of people try to use this to do optimizations. It doesn't work that well because it's a totally random process. So you don't have like specific tendencies in the system you can explore, but it still allows you to kind of very quickly explore a variety of options. So that's kind of the simplest Wasp aggregation you can think of. And so you can see how very quickly you can go from like just defining parts and rules to create very large aggregations. Now, if you have relatively simple geometries, Wasp allows you to handle pretty easily a few thousand parts. Above few thousand parts, Wasp starts to get slow. And at the same time, most likely your Rhino file also will start to get really slow, and it's going to be a bit challenging to kind of move it around and so on. But so if you have relatively simple parts, and if you rely particularly on these stochastic aggregations, you actually have no computational impact of having more parts. So you can create very large aggregations and the computational time will not be impacted too much. Now, if this is the simplest possible way that we can do that, another thing that we could have a look is, what if instead we want to have a bit more control and not just create this crazy cloud of parts? So that it's where, as I mentioned, fields come into play. So I'm going to open another file. Okay. So this file you see is a bit more complex, but the fundamental part here is just the same. So we still have a simple part that allows you, which has a name and has a certain amount of connections. And on top of that, we have an extra thing, which is an attribute that allows us to store the original geometry. So this is something important to have in mind. Wasp naturally works with meshes. So any BREP you might plug into it will be converted into a mesh. But if you want to keep the original BREP within the part because you need it for rendering or for any other reason, or for, I don't know, editing the faces after aggregation and so on, you can simply use an attribute component and store that in the aggregation as well. What then we have down here is we have a system that allows us to create a field based on the distance from a curve. So I'm going to hide the aggregation briefly, and this one too. And so what we do is we kind of provide a curve as an input, and we then create a box around it, which kind of defines the limit where our aggregation will happen and will be contained inside. And we then go and kind of fill this box with points. Now, this is something really important that I think a lot of times people miss. The resolution of this field is fundamental because it has to match the resolution of your parts. If your field, the distance between the points in your field is much bigger than the size of your parts, often your aggregation will get stuck because it can't reach the next part. So what we are doing here simply is we are computing a distance of each of those points from our driving curve. And for you to see, what we can do is we can have a look. So you don't see that, but what we have done is we have created a field, and you can see we can explore that here. So where we see that when we raise this one, this is kind of an ISO curve. And we can actually recently in Wasp, this is a bit of an older file, but we can also see an ISO voxel. So you can see that as I scale down, the number of parts shrinks. And these are the areas where my values are the highest. And as I go far away, they become smaller. And this fundamentally approximates the process in which your aggregation will grow. So if we then use this field in a field-driven aggregation, that is what we have here, you'll see that what happens is if I start from a small number of parts and I start increasing this one, my aggregation kind of starts growing along my curve. And then as it reaches kind of covering the whole curve, it's going to start kind of thickening around it. And so this allows you to very quickly edit an aggregation. And so if, for example, now I go and modify my curve, it's going to take a second because the field needs to be recalculated. But if I now reset my aggregation is now approximating that curve. So you can see how you can very quickly go from just defining a simple geometric driver to kind of approximating that driver with a set of very complicated parts. Now, I'm just going to show you one more thing, just that you can see. And what I wanted to show you is that this is a tutorial that I've been doing for Digital Futures a few months back. And you can, if you go on the Digital Futures YouTube channel, you will find the full video tutorial where I show how to describe this. But this is just for you to show you how much more detail and control a Wasp file can allow you to do. So in this case, we have an aggregation that is made of 2 parts. But what you can see is that these parts have way more complex geometries, but these geometries are not actually the geometry that is used by Wasp per se to do the aggregation, but they are attached to the part as attributes. So as you can see here, the actual part geometry is super simple. It's just, in this case, for one of them, it's a box. And for the other one, it's just a box with a little kink there. So the aggregation per se is super simple and super lightweight. So, but at the same time, by then attaching attributes to it, we can actually visualize more complex things. We can also make sure, using a component that is called supports, that parts do not cantilever beyond a certain limit. So we do not have parts that are fully flying, but they always have at least one contact point. And we can do that by defining for each part specific lines that need to be intersected with another geometry in order for them to be placed. And lastly, you might have noticed that we also have some of these elements that have a different color, which are this balcony here and this kind of shading device there. These are what's called smart attribute. So they're attributes that are displayed only if certain ways in which this part is connected to other parts are satisfied. So in this case, you can see that with the balconies. So the balconies appear only if this face is free and it's not occupied by another element. So in this way, you make sure that you do not have balconies inside the building, but you just have them whenever you have an outside area. And sometimes you have to see how that happens. There might be some little issues here and there. But generally, this adds another layer of information where you can create a process of aggregation that is actually adaptive and that kind of connects to your own, that kind of allows you to customize according to how your parts are connected. And if I have 1 second more, I want to also show you a little fun thing that I've been recently releasing in the beta version, and which I'm going to do a tutorial pretty soon on, which are transformable parts. So that's something that I've been working on really long ago. So during my PhD, we actually started looking at the possibility of creating modular robots. And this is the digital system that works behind it. So what we can do is we can attach transformations to given parts. And after we did the aggregation, we can actually go and actuate those transformations and actually kind of move that around. And this is something that it's really cool to use with optimization algorithms, because you can start from the base geometry of a part and then start, for example, in this case, there's a Galapagos gene pool, start playing around with it and kind of finding a specific geometry or a specific orientation of the parts that satisfies a certain goal. So if you're interested, you can check it out. It's in the last beta version that is on GitHub. It's not yet on food4Rhino. I'm going to try very soon to release a new version of food4Rhino, as well as make a couple of tutorials on this one. So I guess that was it from my side. And if there's any questions, I'm happy to kind of discuss them and hear what you have.
Very, very nice. It looks very fun. And also, it looks pretty easy to use, no? From what I've seen in your demo. Mm-hmm. Thank you very much. It was a great presentation and demo. And yeah, there are a few questions.
Okay.
Actually, Tsveta and Christoph asks if you plan to add a graph data structure to understand which is the link between components. For example, if part 1 is connected to part 5 or part 15.
It is actually there.
Is there?
It's there. There is a aggregation graph component. It's something still a little bit experimental. I'm using it a lot for research projects, exactly for these kind of things. I'm yet to find the best possible way to do it, but there is a graph data structure, and I'm maybe planning to explain a little bit more how that works. But the way in which it's built internally is just a very simple dictionary of dictionaries in Python. So it's it can be automatically translated into, let's say, a typical network data structure used in Python. So, for example, it works automatically with libraries like Network X that allows to do like graph analysis and manipulation. And it's still a little bit hidden, but if you look into the source code is there, and if you send me an email, I can send you a pretty tiny Python script. I think it's probably 2-3 lines that would convert it into a graph data structure for then other processing.
That's sense. So as you feel free to contact Andrea by email for any questions or example files. He's very, very friendly with that. So more questions. Yeah, View when asks if we can use blocks, because you said it works with meshes, but does it also work with blocks?
So it does not work with blocks per se, but I've posted on Patreon a tutorial on how to work with Elephant to create blocks. And so the process is pretty simple, because all you do is you create a plane that you attach as an attribute to your geometry, and then you use that plane to then place blocks after the aggregation. So that's a pretty simple process. So you just have a reference plane that defines where your base part is and your base block created from that. And then you aggregate and you keep track of where those planes are. And then you use those as new reference for the new blocks. So it's pretty straightforward if you know how to work with blocks with Elephant.
Nice solution. One more question by Haiming Wang. How complex can be the rules? That is, can there be a rule that is added on top of another rule? Something like, for example, another GH plugin named SGI. Do you know it?
I don't, unfortunately.
Neither me.
But I'm not sure what would be there for. So the rules per se are like, they're just like this very simple text description. So the number of rules that can be defined is unlimited virtually. And it has no impact on performance as long as you use stochastic aggregations, because stochastic aggregation just pick randomly. So they don't care if the list is 1 million rules or 5 rules. If you work with field-driven aggregations, on the other hand, the number of rules impacts performance massively, because if I have 5 rules, when I place one part, I have 5 options of what to do in the next step. And then when I place the second part, then I have 10. And if instead of 5 rules, I have 50, you can see that already it kind of grows exponentially. And so that makes it much more challenging to work with a lot of rules when you're working with that. I am working right now in a research project at the University of Applied Arts in Vienna, where one of the things we're looking at is processes that are more inspired by L systems, or in general, like also like kind of grammars in which you kind of have process of substituting one symbol for another one to generate rules. But everything super experimental at the moment, and I haven't yet figured out like a proper way to kind of do it in a way. But as soon as there's gonna be something, fine. And I mean, I'm not sure if that was the answer that really answers the question, but again, if there's anything more specific, feel free to contact me.
Just follow your developments to
exactly,
see
and that's
if that's available in one of the next versions.
Yeah.
What else? Yeah, this one is by Carlo Michalus Dianowski. Sorry if I pronounce your names not very well, but many different languages here. Yeah, you mentioned the add-on Topos, which stopped working for me some time ago. Yeah, I think they discontinued it. I'm not sure. Did you have any experience with that? And if you did, how did you fix it? Topos?
I didn't use it recently. For me, it always worked.
It always worked.
Yeah, but also Sebastian that developed Topos is a good friend. So
what's his name? Sebastian? What
Sebastian Bialkowski.
No, I don't know.
So he's a good friend. We studied together. So I have a bit of an access. So if you know that there's a problem, I think he's very busy with other things. So I don't know if he's still working on it. But yeah, I honestly, on my computer, it always worked. But I know that other people had some issues with it. But if the other option is, if you look at the example files of Wasp, there's actually 2 example files to work with topology optimization, and one is working with Topos, and the other one is working with Millipede. That also is discontinued, that also has other problems, but maybe one of the 2 works.
If not, try to contact the developers of Topos
exactly.
via, I don't know, which forums or email or through Andrea. Thanks for the webinar and great plugin, says Peter Batsek. Is there an example use case of Wasp Caramba workflow? So Wasp in combination with Caramba?
I would like to do one soon. So I know there are people that have done it. I haven't done it myself. I've done some very simple things. I've done some work with Kiwi as well, mostly in my research work. But yeah, that's again on the to-do list to do a FEM modeling using Wasp.
Okay. By the way, next week there will be a webinar about TR FEM and TR Mesh by Matthias Fuchs, in case you want to watch it. And yeah, Svetan Christoph also comments that good progress on the data graph. It was in there a few years back.
It's I don't exactly know when it's there. I think it's a couple of years that it's there. I think it's version 0.5. It was there.
Okay.
Yeah.
And then a nice question by Marcin Breczyski. What could be a practical application of Wasp in architecture?
So I am working on practical applications of Wasp. So I'm currently involved in a project that is using Wasp as a back end for a system to generate a modular prefab housing. So fundamentally a prefab housing configurator. And that's actually a super practical application because we're really working with a company and kind of working and using that to do this kind of work. There has been some practical applications. Somebody used it to do floor plans. Not really the best application in my opinion, but can be used for something like that. And in general, it's I think it fits whenever it's about repetitive units. So a lot of the work that I've shown is very much looking at repetitive units at the size of a brick. But the reality is that Wasp per se is kind of does not really care about scale. So I've seen also work from researchers that are using Wasp to do modular urban planning. So to kind of think about cities that are made out of predefined blocks and so on. So there are some applications out there already.
Like this line in Saudi Arabia? Could be done with Wasp?
I don't know.
The buildings there inside?
I don't know. Maybe it doesn't sound like the best example of open architecture, but...
What else? Well, hi from Spain, from Juanjo Fernandez. Hola, Juanjo. Bern Hintamaya, thanks you for the webinar. And Krodoshi asks if you could explain attributes a little bit more, because you mentioned there was an attribute for balconies in the example 1, free space 2, and how far the block can reach. Is there more? It's a bit more information about attributes.
Yeah, so I mean, attributes, so the basic attribute fundamentally allows you to attach pretty much anything to a Wasp part. So it allows you to attach any kind of geometry you want. So geometry that Wasp does not necessarily care or understands, it just knows that it needs to carry it around with the aggregation. But it also allows you to attach non-geometry information. So that's why there is an input that says whether the data you're attaching is transformable or not. So
have you tried, by the way, Grasshopper 1 4Rhino 8 work in progress?
Not yet.
Because one of the things that it adds is attributes.
Okay.
So maybe
that could be an interesting thing to do.
Yeah, can do that easily.
Yeah. And so that's what's there. And instead, smart attributes, they are a kind of an improved attribute. It's fundamentally, again, you attach a geometry to a part, but then at the end of the aggregation, like Wasp decides whether to display that attribute or not, based on how the part is connected to other parts. So that was the example of the balcony. So if on the face where the balcony is supposed to be another part is attached, then the balcony is not there. So it kind of goes a little bit in the direction of what's possible to do with monoceros using wave function collapse. Of course, that's much more really focused on that, but it works on really this idea of like the way in which parts come together defines whether geometry is displayed or not, or how that geometry is displayed. So monoceros allows much more, let's say, detail control. It's really built on, that's what it does. And these kind of smart attributes kind of go a little bit in that direction of allowing you to change the geometry of the part based on how that's connected to another part.
Yes. For the ones that don't know about monoceros, we did also a webinar a few months ago. So if you search for the food4Rhino webinars list, you will find it. And yeah, we're running out of time, but many thanks. A very good webinar, and congratulations again from Juan Fernandez. Thank you for your answer and for developing Wasp from Carlo Michalus. And the final question by Guillermo Sepúlveda. He was asking where to find more information or tutorials about Wasp. So I just paste on the chat the Wasp food4Rhino page, where he will find also your original website, YouTube channel, etc. Right?
Yeah.
Okay, so many thanks to all of the viewers, and of course, many thanks to you, Andrea, for this very nice presentation and live demo. I think we all enjoyed it a lot, and I saw practical applications. And yeah, let's see if we can repeat this webinar whenever you have a major upgrade of Wasp or new projects to show us.
Yep.
And to the audience, remember that this webinar is being recorded. So if you missed any part, just refresh this website, this link, and you will be able to watch it since the beginning. And see you next week on next Thursday again at 5 p.m. There will be a webinar about TR-FEM and TR-Mesh with Matthias Fuchs. So thank you, everyone, and have a nice evening or a nice day, depending in which part of the world you live. Thank you. Bye.
Thanks, everyone.